All right, make sure that you are opening up your notes. I'm going to send the links in the chat. Here is the first link, and here is the second link. One will work, one won't. Go ahead, if you have that open, feel free to raise your hands, and let's go ahead and go over these answers. So yes, when we calculate momentum, again, we need to take the mass, which is measured in kilograms, times the velocity, which is measured in meters per second. So that would mean I'm multiplying 0.15 kilograms times 31 meters per second, and I should be getting 4.65 kilogram meters per second. Again, that is our unit for momentum. Excellent, that is the correct answer here. Go ahead, give me a smiley or an emoji in the chat if that makes sense. Again, we were a little bit slow to get that one started up, so I want to make sure everyone is confident with that. Perfect. All right, so let's go ahead and go over some announcements.
All right, so just as always, guys, please don't share any personal information during class. All right, we are going to require your participation, and these Class Connect sessions are always recorded for learning purposes. All right, today here is Wednesday, right smack in the middle of the week. Tomorrow is a recording day, and then we'll have one more work day for the project on Friday, which is due on that same day. All right, in terms of our units, today we're going to learn about something called impulse. So impulse is going to incorporate some different variables. All right, we're going to learn how to define impulse. We're going to understand the equation for the impulse / momentum theorem. We're going to do some calculations about it. And then we're going to provide examples of how to decrease force during a collision.
All right, I'll send out those links again in case you haven't seen them yet. You can always scroll up though. It's also in your grades tab. Here is the Larkin link. Here is the Bengal link. We need 100% participation, so raise your hands. Let us know you have it open and ready to go. Again, you can do notes at any time for notes credit, but if you want attendance, you need to do them during class while passing them. So if you want both the notes and attendance, you need to do it during class and pass them. Thank you, Lena. I see you in the chat. 20 more seconds for everyone else to raise your hands.
All right, so starting off with the brainstorm today, guys. What are some of the features in modern day cars that keep you that keep you safer during a car crash? Let's just type some stuff in the chat. Sensors, airbags, good. Mallory, but maybe something like that's keeping you safe during a car crash. Like that's preventing a car crash from happening, but during the crash itself. Seat belts, awesome. Anything else besides seat belts or airbags? Anything else we can think of? Got another airbags. Yeah, brakes, good. Brakes. Yeah, so all good answers, but all these things, if we look at them, we said airbags. There's also something called the crumple zone on the front and back of cars where the car will actually crumple a certain distance depending on the force of impact. There are seat belts, which we got, collapsible steering wheels, anti-lock brakes, which means if you brake too hard, your brakes can lock up and you'll skid across the road. So anti-lock brakes prevent that. And electronic sensors. So okay, to whoever said sensors before, Mallory. Okay, you are justified, Mallory. I was wrong. But all these things are doing something in common, which is what they're doing is that they are cushioning or lessening the sudden impact of hitting another object or another car. And that's something that we're going to talk about called impulse. All right, so learning about impulse. Impulse is the product of force applied to an object and the amount of time the force is applied. So our equation for this is going to be I for impulse equals F times delta T. Delta T meaning a difference in time, so a final minus initial. All right, the second definition. In a practical sense, impulse is just the change in momentum of an object. So remember when we had momentum, it was mass times velocity. Okay, the more sudden that you're going to change the momentum of an object, all right, that the greater the impulse it is. All right, and we'll compare the two equations later on. But I'm just trying to get you guys to connect the concepts early on here. So a high impulse in a like say a car crash is something where we want to try to prevent injury, but something with like a low impulse is something like someone just poking you on the back of the on the back of your shoulder or something like that, or throwing a pillow. Exactly. Something with a low impulse is going to feel soft. Something with a high impulse is going to feel hard and sudden. In our notes, we're going to do two of them on the same slide. So for number 2, we're going to write product, and for number 3, we're going to write momentum.
Let's go ahead and talk a little bit about this second definition. So the first definition we already learned is that impulse is force times time, right? Force times change in time. However, our second definition actually also has an equation related to it. So impulse we defined as a change in momentum of an object, and we already learned the equation for momentum, which is mass times velocity. So here we talked about how if you're moving faster, right, it's more difficult to change your motion, you have more momentum, it's going to hurt a lot more. And if you have more mass, again, it's more difficult to change your motion, and therefore you again have more momentum and it hurts more. So today we're going to see about where that hurt comes from, this change in momentum, this collision that occurs. So in this definition, we have a different equation. Impulse equals a change in momentum. Delta right here is the symbol, means change. And again, P is the equation for momentum. So change in momentum. So the way that we can do this is we can calculate this by subtracting the final momentum minus the initial momentum. That's what would be a change in momentum. Smiley faces or emojis in the chat if that makes sense. All right, so based on this definition, I can make an equation here. Based on this definition, I can make this equation. Cool. Now again, we know the equation for momentum. We know that momentum is mass times velocity, right? So I can take the mass times the final velocity minus the mass times the initial velocity. Now, if we know a little bit about math, right, if you have the same term, if you have the same variable in two terms, you can just pull out that variable. So since I have mass in both of these, I can actually just pull that out. And in parentheses, I can have my final velocity minus my initial velocity left over. And this final minus initial velocity is our change in velocity. So I can come back and I can just turn this back into delta V for change in velocity. Now that's a lot of arithmetic and stuff, a lot of algebra there and stuff. So don't panic about the algebra. I just want to prove to you that there's a second equation for impulse. So our first equation was impulse is force times change in time, based on our definition today. But from our second definition, impulse is also mass times change in time. And this comes from the definition of it being a change in momentum. Go ahead, give me a green check, orange X if that's beginning to make sense. There are two equations for impulse based on our definitions of impulse. We have two definitions and two equations. Two definitions and two equations. Excellent. So let's go ahead and talk about then relating those two definitions together. So if I have my first definition where impulse equals force times change in time, and I have my second definition based on momentum where impulse is mass times change in velocity, these things should actually equal each other because impulse here is the same exact thing as impulse here. And so if I just put one equation on one side and the other equation on the other side, this results in something that is called the impulse momentum theory, where my first definition of impulse is on the left and my second definition of impulse is on the right. But because they're the same definition, or because they're the same things, I can actually just set them equal to each other, right? Go ahead and give me a green check, orange X if that's beginning to make sense. Again, I have two equations that are for the same variable, so I can just set those two equations equal to each other. And this is the equation we're going to be talking about today, the impulse momentum theory, which is that F delta T, force times change in time, equals m delta V, mass times change in velocity. And I wanted just to show this to you because I want you to know that this equation comes from somewhere, right? It's sometimes you're like, wow, that's a crazy equation, but the equation actually does come from somewhere. Okay, so let's go ahead and actually try to use this equation. So here's the deal. We started out talking about cars today, and today we're going to continue this theme of cars. So old cars might seem sturdier. Old cars tend to be made out of heavier metals, and they tend to be built kind of like tanks. So they seem like they're sturdy. But the result is they actually have decreased crash time. So because they're so sturdy, as soon as you are in a crash, you immediately feel the impact because that impact gets transferred to you because your car just bounces off of what it's crashing into instead of it crumpling. Okay, so even though they seem sturdier, they actually have less of a crash time. So let's see what this results in our force being. So we have a 900 kilogram old car moving at 30 meters per second, and it crashes to a stop in 0.02 seconds. And our question is, what is the force on the old car? Okay, so let's go ahead and annotate this together. Kilograms is my what? Is this my time, mass, or velocity? Yeah, this will be my mass. Excellent. So I'll plug that in for my mass up here. So 900 kilograms for my mass. And what about meters per second? Meters per second is my unit for what? Yeah, this will be our velocity. So we have 30 meters per second. I'll plug that in for my change in velocity. And then 0.02 seconds, what is this variable? Thank you. Yes, seconds is for time. So let's go ahead and plug that in. 0.02 seconds. Okay, so let's go ahead and take a look at simplifying this. So I cannot yet multiply a variable times a number. All right, so that I'm just going to leave it the same. Force of our old car times 0.02. But on the right side, I definitely can simplify this. 900 times 30. Grab a calculator and tell me in the chat, what is 900 times 30? Thank you, Mallory. Let's get some more answers. 900 times 30. Thank you, Seraphim. Thank you, Jaime. Yeah, so right here, we should be getting 27,000. So let me go ahead and type that up here if my computer will let me. Here we go, 27,000. Now, we want to go ahead and get force by itself, okay? Currently, it's being multiplied by 0.02. Now, in order to get rid of multiplying by 0.02, we need to do the inverse or opposite function. What is the inverse or opposite of multiplying? Yes, this is going to be dividing. So we're going to go ahead and divide by 0.02, and that gets rid of it on the left side. But whatever I do on the left side, I also need to do where? Whatever I do on the left side, I also need to do, yes, on the right side. So I'm going to do the same thing. So divide by 0.02 on the right. So again, grab a calculator. And now, again, starting with the first number, 27,000, divide it by 0.02 and tell me, what do you get? You should get a really big number. What do we get here? Thank you. I see Mallory in the chat. I see Noah, Angelina working. There we go. Yes, yes, yes. Exactly. You should be getting this huge number. You should be getting 1,350,000. And this is a force, newtons. All right. So 1,350,000 newtons. So just off the top of your head, do you think this is a big or small force to experience in an old car when it's in a crash? Is this going to be a big or small force that you're experiencing? Yeah, it's a big, big force, all right? Let's go ahead and we're going to compare it to a new car in just a moment, which you'll still experience force in a new car when you're in an accident, but it's going to be a little bit different. So this is the answer to number 4. In the first box, please put the number. In the second box, please put newtons. Make sure you actually spell out newtons. You need to include the entire word, all right? So here's our first box. Here's our second box. This is number 4. You have 30 seconds to get that done. Go, go, go. Let's go ahead and take a look at a new car. So a new car has a crumple zone. We talked about that in our brainstorm today. So among having a crumple zone, there's also some other safety features like seat belts, airbags, etc., etc. All of this increases the crash time. So when you're in a collision, this increases the time before you feel the impact. Smiley faces, emojis, if that makes sense. All of these things are increasing the time it takes for you to feel the impact in a crash. Okay, now this new car, let's imagine it has the same exact mass, 900 kilograms, and the same exact velocity, 30 meters per second. But this time, it's going to take longer to crash. So this time, instead of 0.02 seconds, it takes 0.15 seconds, which is actually a lot longer than 0.02 seconds, okay? So we want to know what the force is on this new car. So taking a look here, right, we have a mass. It's the same mass, 900. We have a velocity. It's the same velocity, 30 meters per second. And right here, where should I plug in 0.15 seconds? Is this a force or time? Yes, exactly. This will be our time. So I'll go ahead and plug this in for our change in time, which is 0.15. Okay, so again, same process here. I cannot yet multiply force times 0.15. You can't do a number times a variable. But on the other side, I can definitely do this. Now this is going to be the same calculation. So tell me again, what is 900 times 30? You might remember it. If not, grab your calculators and tell me what is 900 times 30 again. Exactly. We should be getting 27,000 again because it's the same mass, same velocity. All right. However, this time our next step is a little bit different. So this time we're multiplying by 0.15. So to get rid of multiplying by 0.15, I need to do what? To get rid of multiplying, I need to do what? Yes, we need to divide by 0.15. All right, last time we divided by 0.02 because we had less time. This time, though, we're going to divide by 0.15. Whatever I do to the left side, I also need to do where? Whatever I do to the left side, I also need to do where? Exactly, to the right side. So I'm going to divide by 0.15 on the right side. So grab your calculators again and tell me this time what do we get? All right, 27,000, that didn't change, but our time did. So 27,000 divided by 0.15, what do you get? Thank you, Noah. Thank you, Kalina. Yes, this is going to be, thank you, Joseph H., 180,000 newtons. All right, now, is this a big force? Yes, but is it as big as our previous one? Our previous one was 1,350,000. Is 180,000 as big? Yes or no? No, it's definitely smaller. So we can see here that in our new car, we're experiencing a smaller force. And tell me in the chat, do you think that smaller force is going to hurt more or less? Again, think about why we design new cars with these things. Do we want it to be more painful or less painful? Yeah, we want it to be less painful. So a smaller force means it's going to definitely be less painful. All right, this is going to be the answer for number 5. Please raise your hands. Again, the first box, fill in the number, which is 180,000. The second box, fill in the unit, which is newtons. All right, this is going to be the answer for number 5. Please raise your hands. You have 20 seconds to fill that out. Let's box this on the whiteboard. Let's put it all together. How do the forces compare when the time changes for the same type of collision? All right, so our old car stopped in 0.02 seconds. So was that a fast time or a slow time? Right, compared to 0.15 in our new car. And this resulted in 1,350,000 newtons. So is that less or more force? And therefore, is this less or more deadly? Go ahead and get your answers up on the board. Excellent. I see Cody up there. Angelina, go ahead and draw that up on the board for me. There we go. See Angelina up there. Awesome. Yes. So taking a look here, the old car stopped in a much faster time, and so it actually resulted in way more force, right? So it had less time, making it faster. So it had way more force and therefore was way more deadly. Let's go ahead and compare that to our new car.
Is slower or faster and resulted in 180,000 newtons. So put a box around slower or faster. Our new car is such that because it's stopping with a greater amount of time, that force is transferred slowly rather than very suddenly, and so you feel less force and it is less deadly to get in a car wreck with a newer car than an old car. All right, that's why the crumple zone is a very important feature. All right, so for 6 and 7, go ahead and mark those answers. 6 is going to be faster, more and more. 7 is going to be slower, less and less. All right, so connecting impulse momentum theorem. So the car example from the brainstorm, airbags, padded dashboards, and crumple zone all help to increase the time that it takes for a collision to occur, which decreases the amount of force that we feel. So the force over time, yeah, so with momentum, if we have a greater amount of time, the force is going to be lessened, right, with our impulse. Or looking at the truck that stops very suddenly and we have a very small amount of time with a large amount of force, it crashes and it crumples all into a big mess. So basically, that's what we're looking for with impulse to make cars safer, is that we want to lessen the impulse, thus increasing the time it takes for it to crash. All right. Let's practice this a little bit. Box on the board. When a parkour athlete jumps from a building, is it better for them to land on their feet or to do a roll, and why? So let's place the boxes on some of these options. They should either land on the feet or do a roll because it either increases or decreases the time of impact. All right, so thank you for the correction. So right, so when people do parkour, they usually do a roll because this increases the time that their body impacts the ground, and so you can reduce the stress on your knees, on your joints, and absorb that impact on the ground easier, and have it not basically not hurt at all. All right, so let's go ahead and raise our hands for number 8.
All right, so on the whiteboard, in a water balloon toss, what will most likely prevent the water balloon from breaking? Moving your hands down as you catch the balloon, keeping your hands completely still, or moving your hands up to meet the balloon. Go ahead and think about what's going to increase the time of impact, right? What's going to increase the length of the collision? Go ahead and box the correct answers up on the board. Go, go, go. I do see some of you in the chat, but get it up on the board just so everyone can see it. Thank you, thank you. Think about what will increase time of impact because that's going to actually decrease the force, right? So increasing time decreases force. Yes, excellent. I see lots of great answers up here. You are absolutely correct. If the water balloon's coming towards you and you move your hands down as the water balloon is hitting your hands, you're actually taking a lot longer for the water balloon to actually feel the impact of your hands. So the extra time means it kind of spreads out all that force, and so your water balloon is less likely to break. Go ahead and give me a green check, orange X if you're feeling more and more comfortable with this concept. Again, the longer time, increased time actually means less force, decreased force. All right, good. So you always want to think about what's going to increase my time in a collision and therefore what's going to decrease my force that I feel so that I survive that collision or so my water balloon survives that collision. This is number 9. Take 20 seconds to answer that and raise your hands. And then the next one you need to complete on your own. So we'll go over the next one and then we'll go ahead and wrap up. All right, so again, this is a Q&A, this is one that you need to do on your own, but if you do need help, we're in the Q&A area. So in boxing, when someone is about to be hit, they may relax their neck and allow their head to move back upon impact, much like with our balloon, all right? This is called riding the punch. Based on what we've been learning in the impulse momentum theorem, which two of the following statements explains the reason behind this technique? So you need to choose one from what's going on with time and one from what's going on with force. Okay, so the time for impact decreases or increases, the force decreases or increases. If you're having a hard time thinking about what's happening, again, think about the crumple zone on a car. What's the purpose of a crumple zone? How does it affect crash time? Does it increase or decrease the time for the crash to be completed? And what happens to force? Does it increase or decrease the force, the pain that you feel? All right, this is number 10. Go ahead and take 45 seconds to work on that and then raise your hands.
Momentum and learn how they can interact with each other. And we provide examples of how we can decrease force during a collision. All right, let's just go on towards submitting our notes. So if you haven't already, go ahead and submit your notes. All right, a couple of you have already told us how well you did. So good job for that. Don't forget to watch tomorrow's recording. And we will see you guys on Friday. If there are no other questions, have a great day.